how the theory was developed and how we use the theory, right? So we'll just recap it quickly. So Tudorson, because we'll see other variants by other authors. 1935. If you remember what he exactly did was the non-circulatory and circulatory components, right? Remember, we have all the way here on the side, we have the no penetration boundary condition, right? We have the d gamma dt equals 0, the law of zero total circulation of gamma equal constant, and we have the Cotta condition. The three conditions, they help to get the singularities. We're solving by the method of singularities, meaning we're satisfying the differential equations by throwing out a bunch of singularities in the domain. These singularities individually satisfy the differential equation, so you don't need to worry about the differential equation anymore, they automatically satisfy. But then these singularities are of unknown strength. I need some conditions to help me to find their strength. So these conditions are always there. The no penetration boundary condition is not negotiable. This condition must be satisfied, right? The flow cannot penetrate the solid. No negotiation about that. The Cotta condition is controversial, but we have no alternative. The law of zero total circulation, we know that it's valid for inviscid flows. So if you care about viscosity, then it's not applicable. Okay? Yes, Lee?
One question about controversial. So what do you mean it's controversial?
Because it's not mathematically derived. It's not coming from a first principle. It's just Cotta condition, as we discussed, came from physical observations. We observed that the flow just come off smoothly from the trailing edge. So let's assume that. It's an assumption, right? And it's an assumption that works perfectly for steady flows at small angles of attack and a high Reynolds number, but not necessarily for unsteady flows. In fact, it's not applicable to unsteady flows. But again, we don't have an alternative. So Tudorson and all the pioneers, they already used the Cotta condition. So let's remember what Tudorson did. For the non-circulatory flow, again, Tudorson heavily relied on the Cotta-Jakovsky, the Jakovsky transformation. So he worked already in the cylinder domain, and then he mapped to the plate domain. So in the cylinder domain, here are the singularities that he assumed, Q of theta, which is unknown. Do you remember, anybody remembers how Tudorson determined the source distribution? What condition helped him to determine the source distribution? Anybody remembers? The no penetration, exactly. So no penetration, which means the normal velocity. So the normal velocity due to motion, this is already known, right? Of x or of theta in the cylinder domain, this is already known. This is the motion of the airfoil. Has to exactly match the normal velocity due to your singularity, so due to your q's, okay? Normal velocity in the cylinder domain is simply the radial velocity, right? And due to our singularity, we spent quite a time, almost one lecture, deriving that VR, or proving that the radial velocity is half of the source distribution, which you have a similar problem in your midterm, but on the flat plate, not on the cylinder. We already did the cylinder one in the lecture, okay? So now you have this left-hand side, and this is the unknown. It's a straightforward equation. This equation is exactly like you said. This is the no penetration boundary condition. The normal velocity due to your flow field is equal to the normal velocity due to motion. Okay? There is no relative normal velocity. The relative normal velocity is 0. Okay? So from here, Tudorson got the q theta, and once you get your singularities, everything is known. From this q, in a very similar way that you get VR, we get v theta, because v theta is the one that gives you the loads through the unsteady Bernoulli. So v, in particular, v theta at theta equals 0 was negative 2 v3/4, the normal velocity due to motion at the 3/4 pole point. In terms of the angle of attack, it's 2u times alpha 3/4. Okay? So like we discussed before, this is not 0, which means that the u at the trailing edge goes to infinity. So this is why he invoked the circulatory component. And again, now it's a new problem. It's a new problem with circulation in the wake. So this is your cylinder. Put one vortex here in the wake at a distance x, large x, corresponding to a distance maybe z in the plate domain. And you need to satisfy too many things. He already satisfied the no penetration boundary condition here, so over there he needs not to disturb it. Meaning the radial velocity was already adjusted, so the radial velocity of the cylinder here has to be 0. And this was a homework problem. In order to do that, this distance is now known, is dictated to satisfy this condition. The radius squared divided by this x. So the no penetration boundary condition was satisfied here. This is the no penetration boundary condition was satisfied here in the non-circulatory component. Now adding this blue thing already satisfied the law of zero total circulation because they are equal and opposite, and it doesn't disturb the no penetration boundary condition, right? Then still this singularity that he added was unknown, right? How he got this singularity, anybody remembers? How he got the value of gamma? How he got the value of gamma? Exactly, the Cotta condition. So the V theta circulatory at theta equals 0, which is exactly this value, plus, it's not circulatory, plus the V theta circulatory at theta equals 0. This is proportional to gamma, right? This equals 0. This is the Cotta condition. So this is function of gamma. Exactly this was 1 over pi b integration from b to infinity gamma wake of z and t times the square root z plus b over z minus b dz. So this is equal to what is coming from here. This was negative actually. So this is 2u alpha 3/4 at any time t. This is what we called what? What we call this equation? What we call this equation? Very good. Integral equation for circulation. For wake circulation. Integral equation for wake circulation and circulation distribution. Okay? For wake vortices, wake vorticity distribution. And you can notice here that if you multiply pi b over there is no. If you multiply pi b over there, this will be your quasi-steady circulation. Okay. So this is like a linear operator acting on my wake circulation. Okay. Give me a wake circulation. You put it in this integral, you get a function of time. The result is just your forcing input, okay? It's just your forcing input, which can be seen as the angle of attack at the 3/4 or your quasi-steady circulation. It's a very hard equation, cannot be solved analytically, even though it's linear. But then what Pedersen did, if you remember, here is the circulatory lift. It was rho u integral gamma wake z over square root z squared minus b squared, again from b to infinity. So what he did, he multiplied by gamma quasi-steady and divided by gamma quasi-steady. So this is what he did. Multiply here by gamma quasi-steady divided by gamma quasi-steady. So his circulatory lift is rho u gamma quasi steady times this integral divided by gamma quasi steady, right? The other gamma quasi steady, he got it from here to satisfy the integral equation. So this is the other integral from b to infinity gamma wake of z and t square root z plus b z minus b dz. Still, this is very hard to determine, this ratio of integrals. Luckily, for harmonic motion, so gamma wake of z and t is gamma wake of z times ei omega t, right? And this may be complex. Then, because the wake convects with the flow, so gamma wake at any z and t is the gamma wake at any fixed location, say the trailing edge, at an earlier time. So t minus the travel distance divided by the convection velocity. So this is z minus b. Which means if you lump these guys together, these two statements together, you get the following. You get gamma zt is just gamma wake bar at the location b, which is a constant. Any constant, you lump it into this constant, and here is the dependence, ei omega t minus z over u. So you already figured out the solution just by the fact that it's harmonic and the fact that the wake convects with the flow mainly by the free stream. So just these two together, of course, due to the linearity of the equation, because if it's not linear, you will not get this thing. Because if it's a linear equation and these two facts immediately give you the solution, we did not do anything, here is the solution. It's just a constant, maybe complex number, that's fine, but it's a constant. And here is the dependence on time and z, okay, on space and time. Then if you substitute back into this ratio of integrals, you get the famous Tudorson function, luckily, okay? So this is, in a nutshell, Tudorson kind of thing, okay? This is Tudorson. So, any question about that? Because we will study today, we will study from a different spirit. We will study the work of von Karman and Sears. It's quite a different spirit. No division into non-circulatory and circulatory, they are lumped together. Quite different perspective and approach, and they yielded the exact same result at the end. We need to get this exposure to different approaches so that if you like to develop your own model at the end, you have more than one way of doing it. Okay? Any question about Tudorson, about just the approach, not the details? Any question about the approach? So let's see what von Karman and Sears did. This is very common in, so nowadays when they try to go back and follow the early steps of the pioneers to develop a new model or something, they go to von Karman and Sears. It's very nice paper, 1938. Tudorson was 1935. I wrote this already. Like I said, they did not divide the flow into non-circulatory and circulatory. They just dealt with it at once, and they started with the vortex setup, which is very similar to Tudorson. Again, we have Joukowsky transformation, so we'll work on the cylinder domain. Here is a vortex in the wake, and we want to study, because remember, unsteady aerodynamics is all about the effect of the wake, right? So from the get-go, here is a vortex in the wake, and the same was with Tudorson, right, in the circulatory part. Here is a vortex in the wake, and we want to study its effect on the cylinder. Remember here the triplet that we have. We have the no penetration, we have gamma is constant, or d gamma by dt is 0, and we have the cutter. These three guys, they help you determine your the strength of your singularities. So they introduce the gamma here, unknown strength, of course, but whenever we introduce a singularity in the fluids of unknown strength. And here's what they did. They said, okay, this gamma is the distance x, right? Well, for the cylinder to be streamlined, here is another gamma, an image vortex of the same strength. And what distance? This is b over 2. What distance is this? It's the radius squared over 4x, so this is very similar to the Dawson setup, right? Now, by this setup, what did we satisfy out of these guys? What did we satisfy here? What did we satisfy? Did we satisfy the no penetration boundary condition?
Yes.
Kind of. In the sense, we did not feel any motion yet. We did not satisfy the motion. But we did not disturb it at least. So the cylinder is a streamline, that's fine. But it's not moving yet. Okay? It's not moving yet. So kind of. It's not completed. Did we satisfy the law of zero total circulation?
Yes.
Yes, very good. That's right. Did we satisfy Cotter condition? No, not yet. Okay. So we still need or can make use of the no penetration boundary condition and the Cotter condition. Okay, we already did this before and we obtained the V theta due to this gamma, the V theta on the cylinder. Due to this gamma, this is exactly copied from Theodorson's effort that we did before. V theta at any theta was negative gamma over pi b x squared minus b squared over 4 divided by x squared plus b squared over 4 minus bx cosine theta. Okay? And actually, if you write it in the, there is a relation between large x and z in the plate, so you will get this equation v theta at any theta on the cylinder, it's negative gamma over pi b square root z squared minus b squared over z minus b cosine theta, after you use the Joukowski transformation. Just replace things. This is exactly equation 5 in the paper, okay? So, what he said, okay, this does not satisfy the Cotter condition, right? Because V theta at theta equals 0, the trailing edge is negative gamma over pi. If you put theta equals 0, so this will be z minus b, yes, exactly, 1, z minus b, so z minus b all square under the square root, and this is z minus b, z plus b, right? So you can do this thing and you have z plus b over z minus b. So this is not 0. So at the trailing edge at theta equals 0, we have already some v theta here, correct?